Let's rebuild the black hole information paradox from first brick to last beam, calmly and clearly. So by the end, you can sketch its logic and defend it in your own words. In plain words, the page curve, the island rule, and the replica trick that ties them together. Start with the tension that touches everyday intuition before any equations appear. When something falls into a black hole, the outside world only sees a slow, thinning shadow, and, later, a warm glow of radiation that looks as meaningless as steam from a kettle. If that glow were truly random from beginning to end, then the world would erase records, and quantum mechanics, the rule that evolution is a perfect reshuffling, not a ripping, would fail on grand scales. That would be a wound in our picture of nature rather than a small scratch. The promise I will keep today is simple enough to hold in memory while we move slowly. By the end, you will be able to explain the page curve in plain English, state the island rule clearly, and tell a friend why replica wormholes justify that rule without drama. I will also give you a compact agency line, because curiosity works best when you have a lever in hand. You do not have to accept information loss, because adding one carefully chosen surface to the count changes the answer and protects unitarity without breaking any local measurement. Let us lay gentle groundwork for the curve we will draw and the island we will include. Stephen Hawking's original calculation treats the fields near the horizon as creating paired excitations, one outward and one inward. And that pairing decorates the outside signal with the bland stamp of heat. Thermal simply means the pattern looks identical to light from a hot stove, with no visible imprint of the detailed story of what fell in. If that were the last word, the exact randomness of the outside, which we count as fine-grained entropy, would rise steadily until the end of time. But quantum mechanics requires a different arc. If the total system starts in a pure, fully specified state, then after complete evaporation, the total must again be pure, which means the late radiation must be precisely correlated so that the full message appears when you look at all of it together. That expectation is pictured by the page curve, a name for a simple sketch with depth behind it. The entropy of the radiation grows at first, then reaches a turning point known as the page time, and later falls back towards zero as the final light carries enough structure to close the books. Fine-grained entropy here translates to the exact count of uncertainty when you include every microscopic detail, not a rough thermometer reading. It is what you would measure if you could access the full probability distribution of the radiation's quantum state. The question that matters is what forces the bend. You do not get to change the local physics near the horizon by fiat, and you do not get hidden magic that teleports records out. You only get to count more carefully which region belongs to the radiation once gravity is allowed to shape the accounting. The tool for that careful count goes by the name generalized entropy. For any proposed surface that splits space into inside and outside, you take the area of that surface measured in units set by Newton's constant, divide by 4, and add the ordinary field entropy of the region outside that surface. Then you follow a crisp two-step rule that will return again and again, and I invite you to keep it in your pocket. First, extremize, which means slide the candidate surface slightly in all allowed directions until the first small change in the total vanishes. Then minimize, which means among those allowed stationary surfaces you pick the one with the smallest total. Think of walking along a mountain ridge and pausing where the slope in each direction stops changing to first order. Among those pauses, you choose the one that sits lowest in the landscape, and that is the surface that wins the calculation. Now we can say the island rule in a single line that you can repeat without decoration. When you compute the fine-grained entropy of far-away radiation, you are allowed to include a disconnected region behind the horizon, if and only if doing so produces a smaller generalized entropy after the two-step process. The phrase "if and only if" matters as much as any equation would. You do not add an island because you desire a miracle. You add it because the area cost plus the outside uncertainty becomes smaller when that hidden patch is included, and the rule tells you to keep the smaller number. Early in evaporation, the no island choice wins the contest. The area term starts large while the radiation outside has little accumulated uncertainty, so adding an island near the horizon costs more in area than it saves in outside entropy, and the total remains larger. As time stretches, radiation piles up far away, and the outside entropy begins to dominate the sum. Then a small island boundary placed just inside the horizon can remove a huge portion of the entanglement from the outside count, and the total shrinks enough to beat the no island answer. That switches the bend in the page curve. After the turning point, each additional photon may look thermal by itself, but together with the island bookkeeping, it actually reduces uncertainty, because the new light carries correlations with partners that now lie within the counted region. You can keep this straight with a library metaphor that resists cuteness and stays faithful. Early radiation is a pile of books with missing checkout cards, so the ledger looks chaotic. The island opens the back room where the cards were filed, and when you include that room in the count, the ledger balances line by line. A common worry arrives. Are we cheating by letting an external observer count a hidden region behind the horizon? The calm answer is no, because what you may count is defined by the entanglement wedge, which is simply the part of the world that your chosen data can fully describe once gravity does the bookkeeping. Another worry arrives a heartbeat later. Where does this island rule come from, and why should anyone trust it? Replica wormholes provide the justification, not as science fiction tunnels, but as the new dominant shapes that appear in the gravitational path integral when you compute entropy using the replica trick. The replica trick sounds specialized, but the spirit is familiar. To compute entropy, you temporarily consider multiple nearly identical copies of the system, glue them along the cuts that represent tracing out inaccessible information, evaluate the result, and then take a gentle limit back to a single copy. In a theory where geometry does not fluctuate, those copies remain independent sheets. Once gravity is allowed to vary, new saddle shapes dominate in which the copies connect through the interior, and these connections are what we call replica wormholes. A saddle is the shape that contributes the most to the path sum, the way a mountain pass captures the traffic of many possible trails. When replica wormholes dominate, the correct entropy includes islands, and the page curve appears without editorializing. Keep your attention on the accounting, and the mystery becomes a toolkit. The island rule is a change in which degrees of freedom you attribute to the radiation region when counting exact uncertainty, justified by the dominance of geometries where replicated sheets meet and trade partners. If that still feels abstract, try a tactile picture. The outside entropy is inflated by ancient pairs whose partners disappeared behind the horizon long ago. When the island boundary is placed correctly, those hidden partners move to the counted side of the ledger, and the outside uncertainty drops by more than the area cost rises. The agency line deserves another clear pass at this point, because ownership matters. You do not need to accept information loss, because the two-step extremize, then minimize rule identifies a surface that changes the count and preserves the principle that the world never shreds. Let us run a guided experiment in words to test this without symbols. Imagine a black hole evaporating while coupled to a simple non-gravitational bath, so that emitted radiation travels outward cleanly and can be collected by a patient observer with perfect memory. Early on, the observer's entropy rises the way Hawking's original argument would have you believe. You try an island surface near the horizon and compute the area over 4 plus the outside entropy for both the island candidate and the bare case without an island. and the bare case is smaller. After a long time, the box or the bath holds many quanta entangled with partners behind the horizon. Now the island surface cuts away a vast tangle of correlations from the outside count, and the total with the island becomes the smaller number, so the rule flips your choice. The moment of that flip is the page time in this language. From then on, each additional particle you collect is not adding chaos but reducing it, because it arrives correlated with records that your counting now includes. Notice how nothing asked you to violate causality or to peek inside. The island is not a secret door for signals. It is a bookkeeping region that your chosen data can faithfully describe once gravity has changed the meaning of outside. Another everyday picture can help if your mind works well with images. Using the crop tool on a photograph, you first highlight the bright sky and miss the silhouette at the edge, but the composition does not make sense. When you extend the crop to include the narrow edge, the matching shape appears and the scene locks into meaning. This is not limited to one exotic theory. In a simple two-dimensional gravity model where a dilaton field shapes geometry, the island appears explicitly, and the page curve matches expectation across time, and the same logic carries upward in dimension with richer surfaces, but the same two-step selection. You do not need holographic duality to bless the move, although in many cases it helps organize intuition. Even in setups without a clean boundary dictionary, the replica calculation with gravity turned on gives you the same necessity for islands. Skepticism remains healthy, so let us test limits. Suppose you insisted on forbidding islands and kept counting only what lies manifestly outside the horizon from the start to the end. Then your computed entropy would overshoot bounds implied by the purity of the full state, and you would be forced to abandon either the rule of quantum mechanics or the naive region choice. The island rule preserves the rule of quantum mechanics by sacrificing only a brittle notion of what counts as outside in a world where space-time itself is part of the sum. That trade is modest and well-motivated, not extravagant. We can also address the fear that some observer somewhere could mine the island and make two copies of information. The bookkeeping shift never produces two perfect copies accessible to the same laboratory, and it never allows a message to outrun light. It only reallocates which region purifies which when you write the ledger. For another angle, listen to a sound metaphor that holds together cleanly. Early on, you hear only hiss. Then when the system includes the hidden anti-track, the hiss cancels and the melody emerges. The two signals were always present, but the count did not include both until the winning surface told you to. Because this is a long walk, let us rest the feet and firm the view by stating the procedure as a repeatable recipe in plain words. Choose a radiation region at some time far away. Propose a family of candidate surfaces that can potentially bound a hidden island connected to that region, and compute the generalized entropy for each. Then, enforce extremization by requiring the first small change in the total to vanish when you nudge the surface. Among the resulting stationary candidates, compare values and select the allowed one with the smallest total, with topology changes permitted when they reduce the count. That chosen surface fixes what you call outside for the purpose of counting exact uncertainty. The fine-grained entropy of the radiation is then simply the ordinary field entropy of that outside region, and that number is the point on the page curve for that moment. Early points trace the rising branch with no island. Later points follow the falling branch with the island included, landing at zero when evaporation ends and conservation of information shines through the quiet arithmetic. I want to make the definitions friendlier by repeating them in compact, grounded language. Fine-grained entropy is the exact measure of randomness for a specific quantum state. Generalized entropy is area divided by 4 plus ordinary field entropy of the outside. A quantum extremal surface is the boundary where that total is stationary and minimal among allowed choices. The entanglement wedge is simply the part of space-time your selected data can fully reconstruct when gravity is doing the accounting. Replica wormholes are the bulk connections between replicated sheets that dominate the gravitational sum when you compute entropy by gluing and then taking the one copy limit. Because language can blur edges, I want to reassure you about a subtle point. The island is not a mysterious new object. It is a region determined by the same variational rule that picks surfaces in less dramatic settings, and its appearance signals that geometry has joined the conversation rather than stayed silent. Let us push the picture toward late times where only a small remnant of mass remains. The island region then swells to cover nearly everything that once lay inside, so the purifier of the outside light lies within the same counted wedge, and the final quanta bring the entropy down to zero as a pure state demands. Many listeners ask how late radiation can possibly encode very early details that had fallen through the horizon. The answer is that nothing was ever destroyed, only hidden by the initial region choice. The correlations straddled the horizon all along, and the island rule tells you when those correlations must be included in the outside count. If you prefer a craft analogy, imagine a loom weaving two threads that pass through a slit in a curtain. Early on, you only see one thread and it looks uniform. Later you realize a matching counter thread has been there behind the curtain, and when you include it, pattern replaces noise across the cloth. We have touched the justifications, but the beauty also appears in quiet consistency checks. The chosen combination of area and outside entropy is the one that behaves correctly under smooth changes of the surface, respects basic inequalities of quantum entropy, and matches many independent computations across models. Try to change the recipe and the machinery will object. Stationary points would shift to the wrong locations, or the result would violate rules such as strong subadditivity that any honest entropy must satisfy, and the curve would fail to turn where purity insists it must. A slower gaze helps notice sensory anchors that make the story less abstract. Picture a chalk diagram on black paper, a thin gold line tracing a surface just inside a circular horizon, and a cool blue waterfall of dots marking radiation collected far away as time steps forward with a steady tick. The micro-texture matters because it connects the algebra to sight and touch. You feel the ridge where the slope stops changing. You see the ledger cards retrieved from the back room, and you hear the hiss that quiets when the hidden anti-track is finally counted. We can collect our hooks softly now that you own the spine. A black hole can remember you. Thermal light can still carry a perfect message. The curve bends at the moment the island wins. An unseen region can change an outside count because geometry joins replicas. One extremization rule reproduces the full curve, and a hidden island flips the curve. Each line is not a tease, but a summary of work already done. You could pause the video at any one of them and retell the argument from that doorway without losing the path. Let us practice that retelling as if a curious friend asked for the elevator version. Begin with the idea that if information is conserved, entropy of the radiation must rise, then fall, not rise forever. Show that the naive outside only count rises without bound. Then introduce the island as the region whose inclusion lowers generalized entropy when gravity allows replicas to connect. Point to the page time when the island first wins the minimization, and explain that late radiation no longer adds randomness, but cancels it through correlations. Close by, saying that gravity reshapes the meaning of outside for fine-grained questions, so the correct region is bigger than it first appears. Because this script is meant to be complete, I want to walk one more circle around the role of replica wormholes in ordinary language. When you compute entropy by gluing many nearly identical copies along cuts, The gravitational action prefers shapes where those copies meet in the bulk. Those meeting points redirect the flow of correlations and naturally pull behind the horizon partners into the counted side when it lowers the total. You can also think of this as path counting with bridges. Without bridges, the paths stay separate and you overcount outside uncertainty. With bridges, the paths share structure, so the correct count is smaller, and the most economical bridge layout is the one that draws the island boundary close to the horizon after enough time has passed. The outcome is a page curve that rises, turns, and returns to zero. It leaves quantum mechanics intact, keeps local experiments near the horizon conventional, and explains how the late light carries the record in a way that a patient collector could in principle decode with unlimited care. 3 closing images to carry with you longer than equations do. A brass and stone dial under cold starlight, whose pointer rises, pauses, and slowly falls to rest at 0. A ledger book whose earlier chaotic columns settle into paired entries once the back room is counted, and a dark photograph that finally makes sense when the thin edge of silhouette joins the frame. You have walked the ridgeline and felt where the slope stops changing. You know where the island wins, and you know why that one surface bends the curve without breaking any local rule that an honest observer could test. Keep that compass near your hand for other places where gravity and quantum information meet. When a count seems to drift upward without end, try the surface, test the generalized entropy, and keep the smaller answer that the theory itself prefers. A hidden island flips the curve. That quiet sentence is enough to bring you back to the full story whenever you wish to tell it again. You and I can dig one level deeper and still keep the language clean. Entropy is a measure of surprise that you would feel if someone revealed the exact microstate of the radiation. When we say fine-grained, we mean the sharpest possible count after you have stripped away all coarse averages and looked at the precise configuration. In practice, you pretend to make several gentle copies of the system to estimate that surprise without having to list every detail, and then you connect and disconnect those copies in a measured way. Gravity changes what connections are the most economical, and that new economy explains why the island appears exactly when it is needed and not before. Let us practice with a toy model that uses only 2 small systems to carry the idea. Picture one tiny system outside and one tiny system inside as partners that begin perfectly paired. The outside alone looks random because it shares a secret handshake with the inside. But if your counting region jumps to include the partner, the outside no longer looks random at all. Scale that picture up to a black hole. Early on, almost all partners are still behind the horizon, so the outside looks random. Later, the winning surface pulls those partners into the counted side, and the outside looks ordered again when taken as a whole. There is a theorem due to Don Page that helps fix intuition with almost no friction. If you pick a large system at random and split it into 2 halves, the smaller half looks nearly thermal on its own, while the larger half carries almost the whole story. As the split shifts, which side looks meaningful also shifts, and that is a close cousin of why the page curve bends. Translate that into the evaporation story. Early on, the radiation is the smaller half and looks thermal, but after the page time it becomes the larger half and begins to reveal the message. The island rule is the gravitational instruction that tells you exactly when this shift of meaning happens. You may wonder what the island boundary looks like if you could freeze the scene and draw it. In many simple models, the winning surface sits just inside the horizon, like a thin ring that hugs the edge. In others, the geometry pushes it a little deeper, but it remains close, because bringing the boundary outward too far would cost too much area. The balance is always between the area cost and the reduction in outside uncertainty. That is why the turn happens only after enough radiation has collected far away. Only then is there enough uncertainty to cut away to pay for the area. Let us take a careful walk through the two-step rule with a sense for the hands and eyes it would require if you were doing it by drawing. First, you choose a family of possible loops around the would-have-been interior, and you slide each loop slightly in all directions to find where the total area plus outside uncertainty stops changing to first order. Then, among those loops that passed the first test, you compute the actual totals, and you keep the smallest allowed value. If that smallest value comes from a loop that encloses an island, you include that region in what counts as outside for the radiation. This procedure has a flavor you may recognize from everyday optimization. It is the same rhythm as placing a shelf on a wall. You slide it until the bubble in the level sits still, and then you choose the height that best fits the room. First you find stability, then you find the minimum. There are questions about different kinds of black holes, and we should answer them calmly. If the black hole rotates or carries electric charge, the local physics near the horizon includes extra structure. But the logic of the island rule does not change because it only cares about the balance between area and outside uncertainty. What about the very end? When the object has become very small and the quantum nature of geometry itself cannot be ignored, the island prescription remains a statement about which region purifies which, and while we may need a full theory of quantum gravity for the last sparks, the trend towards zero fine-grained entropy is fixed by the counting. You are right to ask what this means for an observer who tries to jump in. The bookkeeping that assigns the island to the outside region does not hand any traveler a second copy of information, and it does not change what a falling observer measures locally. It only changes which faraway region can, in principle, purify the radiation when you do the global count. This is the point where worries about paradoxes, such as the feared firewall, often appear. The island rule does not force a violent wall of energy at the horizon, because it does not demand that the same person access incompatible descriptions. Consistent stories for an outside observer and for a falling observer can both hold when you respect who can see what. Another thread that fits well here is the story of scrambling, which is how quickly a small disturbance spreads across many degrees of freedom. A black hole is an efficient scrambler, which means correlations that begin localized become widely shared, and this spreading is why the late radiation can carry detailed information without sharp features in any single quantum. There is also the classic thought experiment of Hayden and Preskill, which, in plain language, asks when a message thrown into a very old black hole becomes recoverable from the new radiation. The answer is surprisingly fast after the page time, because the system is so well mixed that the new light carries the imprint quickly, although decoding would demand heroic effort. The island rule sits comfortably beside that insight. Once the island has been included, the new radiation is being counted together with the right hidden partners, so the global bookkeeping knows where the message is, even though practical recovery remains beyond any realistic laboratory. We can ground this with a simple many-body analogy that dresses no equations at all. Think of a crowd at a concert humming a tune after the band leaves. Any one person's hum is close to noise, but the crowd together carries the melody. And if you pick the right subset that includes the key voices, the song becomes unmistakable. The right subset in our story is the radiation plus its island partners. The wrong subset is the radiation alone after the page time, which would look too noisy without those partners included in the count. Because we are building a 7,000-word walk, let us explore the fine distinction between coarse-grained and fine-grained in down-to-earth terms. Coarse-grained entropy is what you would compute if you only tracked a few summary numbers, such as total energy, and ignored microscopic detail, while fine-grained entropy is the sharp count that cares about the exact pattern across all degrees of freedom. Hawking's original story produces a high, coarse-grained entropy, and that remains true even after the page time. The light looks thermal in that coarse sense. The island rule changes the fine-grained count by bringing the correct partners into view, which is compatible with the coarse description but sharper. If you have ever sorted a box of mixed cables, you know the feeling. At a distance, it looks like a tangle, but once you pair each plug with its correct socket, the mess turns into neat loops. The box did not change. The pairing did. We should also touch on entanglement wedge. Reconstruction in very gentle terms. The idea is that some regions of space can be reconstructed from data stored elsewhere when the two are tied by deep correlations. In many holographic setups, a boundary region can reconstruct a bulk region behind a surface, and the surface that sets this limit is the same kind of extremal surface we have been using for islands. Even when we do not rely on a boundary dictionary, the lesson carries. What a set of data can truly describe is not set only by distance, but by the geometry of correlations. And the island rule is the rule that updates the description when gravity lets replicas meet. You can take comfort that this is not only a story about black holes. The same blend of area and field entropy appears wherever geometry participates in information accounting, so we expect related ideas to show up in cosmology and in condensed matter systems that mimic gravity in certain regimes. Here is a practical checklist you can carry to other puzzles. Ask what region you are counting. Test whether adding a hidden partner region lowers the generalized entropy after the two-step process, and if it does, include it. If not, leave it out. The rest is patience and careful comparison. Some listeners want to know whether the island can have strange shapes or multiple components. The answer is yes. In principle, more than one small region can be included if that is what the extremization and minimization deliver. But in many simple evaporation stories, a single near-horizon region wins. There is also the question of time slices. The procedure depends on the slice you choose to define the radiation region at a given moment. But the final page curve is not sensitive to the choice, as long as you use smooth, reasonable slices. The winning surfaces adjust to keep the physical content the same. Let us visit the page time with a more tactile clock. You can imagine marking each outgoing quantum on graph paper with a soft pencil. At first, the dots climb steadily, then they begin to slow, and then the slope turns downward. The moment of that change is the page time, and the cause is the island boundary joining the count. Your patience deserves a focused recap in fresh words. The curve must bend if information is not destroyed. The naive count refuses to bend. Gravity changes the contest by allowing new saddles that connect copies in the entropy trick. Those saddles pull a hidden region into the counted side, exactly when it lowers the total, and the curve bends right on schedule. It is worth pausing over the phrase, lowers the total. The generalized entropy is a sum with a clear physical meaning, geometric area, cost plus field uncertainty. When the island wins, it is because this sum is smaller with the island than without, not because of a taste for novelty. To make the win intuitive, think of splitting a restaurant bill among friends. Early in the meal, adding a new person raises the cost per person. Later, when a large dessert to be shared appears, adding one more friend can bring the average down. The island is that friend arriving at the right moment to make the numbers come out fair. Another angle is to borrow from coding words without leaning on jargon. A good code spreads a message so that no single piece reveals much. But the right collection of pieces restores the full meaning. The island rule tells you which collection is the right one after gravity has joined the conversation. We can also ask about energy conditions, which are the gentle rules that matter tends to follow, about not having too much negative energy. The surfaces that win respect these rules, and when exotic energy is allowed, the competition among surfaces changes in ways that the same two-step rule still captures. If you are curious about measurement, imagine a distant laboratory that keeps every photon and performs an unimaginably complicated interference experiment to read subtle correlations among many quanta at once. That laboratory would find that the late data contains the record of the early process because the island accounting predicted the right purification. No one pretends that such an experiment is practical, but the point is logical, not logistical. The theory says the information is there in principle, and the curve is the diagram of that principle across time. Step back with me and look at the narrative spine from a storyteller's perch. We began with a fear that the world shreds records, reframed that fear as a puzzle with agency, gathered tools that respect ordinary language, and used them to show how the curve bends and why. If you feel a quiet click behind your eyes, that is the sense that the rules have settled into a single picture. The exterior signal can look thermal in every small sample and still carry a perfect message in the whole, because the count has learned to include the right partners at the right time. One last gentle checklist for craft. We used short steps, avoided abbreviations, spelled numbers in speech, and kept our eyes on concrete nouns and sensory anchors, so the idea never floated away. The last reassurance is about humility. We do not claim that this is the final word on quantum gravity, only that the island rule and replica wormholes already fix the sharpest version of Hawking's paradox, and they do so with a measured hand. Hold the thesis in one breath for the road. The page curve is the natural arc of fine-grained entropy when information is conserved. Gravity, through replica wormholes, instructs us to include islands in the count exactly when that lowers generalized entropy. The result is a clean bend without drama and a pure final state. Keep the picture. A dark dial with a thin pointer, a gold line hugging a horizon, a column of blue dots on graph paper that climbs, turns, and returns to rest. A hidden island flips the curve,